general guidelines for sketching. I think more or less all the rules were covered, but for two. Let me give those two rules quickly and then go on to the complete examples. And through these examples, I think all the rules will be properly revised. The two pending rules, the numbers I don't know, what was the list you see, but let us not worry about the numbers. The two pending rules were the angle of departure from a complex pole or angle of arrival at a complex zero. If you go through your notes, you will find a root locus of this type coming in your notes, because I had taken this example. Let us say that these are the two poles and here is a 0. Now, if you apply all the rules of root locus sketching, you find that this total thing is on the root locus plot, this segment. And if you apply your rules for break away or break in, you will find that there is a break in point over here, an approach point over here, and the root locus starting over here breaks into the real axis, and these are the two root locus branches, one going this way and terminating at the 0, and the other going this way and terminating at the infinity. Let us say k is the root locus gain, k is equal to 0, k is equal to 0, and infinity here, k tends to infinity here. This is a root locus sketch which is already there in your notes. Now the question is this, that well, in this particular sketch, fortunately it can be proved. Rather, I will like to leave this as an exercise to you to prove that this complex root locus portion is a circle. So if it is a circle, you can easily make the root locus diagram. But otherwise, in general, you will very much like that the root locus, when it leaves this particular complex poles, does it leave this direction, in this direction, in this direction, or in this direction? For example, it could go this way, it could go this way, or any direction it can take in general. As I am telling you that for this particular numerical example, you can prove in general that the complex root branches are circle with this as radius, and hence you don't need the direction. But since I have taken this very example, let me now exemplify the direction through this example itself. The process is like this. It says that you get the angle contribution at this particular pole. Let us call this as theta 1 due to this 0. You get the angle contribution because of this pole at this point, and let me call this as theta 2. The net contribution at this particular pole is how much, please? It is theta 1 minus theta 2, because theta 1 is because of a 0 and theta 2 is because of a pole. So theta 1 is positive and theta 2 will be negative, being in the denominator. So the net angle contribution at this particular pole, because of the other poles and zeros, in this particular case is theta 1 minus theta 2. And the rule says that the root locus will leave this particular pole at an angle phi is equal to plus minus 180 degrees into 2q plus 1 plus phi p, let me call it, plus phi, where phi is the net angle contribution due to all other poles and zeros at the complex pole under consideration. I repeat the rule, please. Theta 2 in this figure is naturally 90 degrees. But otherwise, yes, it is this particular pole I have taken. I have drawn a vector to this particular point under consideration, and this is the angle contribution of this pole at this point. Okay, so I have drawn a horizontal line, and this is the angle. In this particular case, it is too obvious because these are the complex poles. This particular angle is theta 2 equal to 90 degrees. In general, let me take a general situation, I think, so that the specific situation is avoided. This is a complex pair. Here is a pole, here is a 0, another pole. And you want, in this particular case, now there is no circle business. You cannot say in general that the locus leaving this particular point is a circle. Now what you need is that a root locus will start from k is equal to 0. I really do not know which direction it will go. I want the direction of takeoff from this particular point. It could be any of the directions as far as total 360 degrees angle is concerned. And now the direction I say, suppose it is phi p. How do I determine how do I write this phi p? Please see that the phi p angle will be written this way. Draw a horizontal line, draw an angle phi p. So if I determine the angle of departure at phi p, so it means the root locus will leave this way at this particular point. Now this angle of departure phi p is given by this formula. I am repeating this formula for your benefit. Phi p is equal to plus minus 180 degrees into 2q plus 1. You can take q is equal to 0 also, because q is equal to 1 means a shift by 360 degrees, which does not make any difference as far as the angle is concerned. I am simply writing the general formula. Otherwise q is equal to 0 will suffice. Plus phi. What is phi? Phi is the net angle contribution at this particular pole due to all other poles and zeros. Note this point please. Phi is the total angle contribution at the pole under consideration due to all other poles and zeros. Now let us see how to determine phi. Consider this particular pole. Draw a vector here. This is the angle contribution due to this pole. However, please note, since this is a pole, the angle will come with a negative sign. Take this 0. This is the angle contribution. Due to this 0, the angle will come with a positive sign. Here is the angle contribution due to this pole, and lastly, this is the angle contribution due to this pole, which again obviously is 90 degrees. So calculate the total angle taking suitable algebraic sign into consideration, positive sign with the zeros and negative sign with the pole. Let us say that total angle turns out to be phi. In that particular case, the root locus will leave this particular pole at an angle phi p given by this formula. Okay, I hope this, and this will be exemplified. Let me not give an example here. I am going to take a comprehensive example in which all the rules will be revised. So naturally this rule will also suitably come up there. Okay. Similarly, you may have a situation of this type. Let us say you have two complex zeros, and let us say these are the two poles here. A typical situation I take this way. Now you see that a root locus starts from k is equal to 0, k is equal to 0. There are two zeros available, so naturally it will terminate at these 2 points. I do not know the root locus shape, but at least I know that the termination will be at these 2 points, whatever directions it may take. And these portions of the root locus branches will be determined by other rules which I have already given to you. Now I want to concentrate on the rule as to which way will it approach the 0. Will it approach the way I have already drawn, or will it approach this way, or will it approach this way? Which is the way it will approach the 0? And that is given by the following relation. Phi z equal to the angle at which the root locus branch will approach a complex 0, okay, is equal to again plus minus 180 degrees to q plus 1, okay, minus phi I take, where now what is phi? The same thing, the net angle contribution due to all other poles and zeros at the 0 under consideration. In this particular numerical, for example, you see, you just take this 0. So the net angle contribution is double of this because there are two poles. Suppose this is theta 1. So the net angle contribution at this 0 is minus 2 theta 1. You join this 0 with this, make this vector, and the net angle contribution due to this 0 is theta 2, which is equal to 90 degrees. And therefore, in this particular case, your phi z, the angle at which it will leave this complex 0, is equal to say 180 degrees minus or plus sign you can take minus phi. Phi is theta 2 minus twice theta 1. Theta 2 is 90 degrees in this particular case with a positive sign, minus twice theta 1, this being a pole appears in the denominator, so twice theta 1 will appear this way. This is the net angle contribution. This is the way it will leave. So it means if I have the phi z angle available with me, I will draw the phi z angle like this. This is phi z, sorry. this is phi z. If it approaches the way I had drawn earlier, if it really approaches through this particular way, then the phi z, the angle at which it approaches the origin, approaches the complex 0, is given by this particular direction. So, this becomes the angle at which the root locus branch approaches a complex 0. Okay. Lastly, you will recall an example we had taken, Gs equal to k over s into s plus 1 into s plus 2. For example, take it this way. So, s is equal to 0, s is equal to minus 1, s is equal to minus 2. You apply your rules, you will find that this is one branch going to infinity. You find that this segment lies on the root locus, and hence there has to be a breakaway point. So, these are the directions, and therefore, the root locus most appropriately will go this way, that is asymptote, angles, etc. you will determine. The last rule which I want to give you is the following, that you can determine the point of intersection with the imaginary axis using the Routh-Hurwitz criterion. Okay. In this particular case, what you will do, for example, the characteristic equation of the system is s squared plus, help me please, 3s plus 2 plus k equal to 0. This is s cube plus 3s squared plus 2s plus k equal to 0 is the characteristic equation of the system given Gs. Make a Routh table. I am repeating this because in tutorial class there was a little confusion. You are not remembering this point, that is why I am repeating. If you make a Routh table, it is 1, 2, 3, k. Okay. So, continuing with this, it is 6 minus k divided by 3, k. Now, you know that the system will be stable for k greater than 6, for k less than 6. The system in this particular case is stable for k less than 6. So, at k equal to 6, you find there is a case of the row becoming all 0. So, if I take k equal to 6, this element becomes 0, this missing element is automatically 0, which corresponds to a situation that an auxiliary equation is the factor of the original characteristic equation. An auxiliary equation you make from the previous row. Looking at the previous row, you get 3s squared plus 6 equal to 0 is the auxiliary equation, or equal to as is the auxiliary polynomial. 3s squared plus 6, because k is equal to 6 gives you all 0 row, you have to go to one previous row, and 3 into s squared k into s to the power of 0, the even order of s, will give you this polynomial, and therefore the roots of this polynomial are the roots of the original characteristic equation. As you find that the roots are s squared plus 2 equal to 0, or s is equal to plus minus j under root 2. These are the roots. So, in this particular case, it is obvious, going back to the original root locus. So, at this particular point, j under root 2 minus j under root 2 and k is equal to 6 is the point coming over here. So, in this particular case, now you find that if you have k is equal to 6 and j under root 2 minus j under root 2 as the points available, so it is a great help to you. It gives a method of sketching the root locus, a rough root locus, because what you had were the following. You had this, for example, these are the asymptotes, you know. This is the breakaway point you have calculated. So, this breakaway point, these asymptotes and these additional 2 points give you a sufficient information to make a rough sketch of this system. This way, all the rules can be utilized to make a rough diagram, and from that rough diagram, the analysis and design can follow. Okay? This is what is the total quota of rules. Okay? And you have not to remember these rules. You see, if you solve a couple of examples, I am sure that these rules will get set in your mind. Now, I will like to give you a few examples. 3 examples are in my mind, 3 different examples. All the 3 examples will exemplify something new. Okay? First of all, I take a comprehensive example to revise all the rules. And this example is, given a unity feedback system with open loop transfer function k over s into s plus 3 s square plus 2s plus 2. This is the example, please. Apply all the rules on this example and let us see what type of root locus do we get. So, the first step, take the open loop poles and zeros on the S plane. So, in this particular case you find S is equal to 0, S is equal to minus 3, and help me please, what are the locations of open loop of the open loop poles due to the factor s squared plus 2s plus 2? Yes? What are the factors please? Minus 1 plus minus j. So, let us take minus 1 over here and okay, I am sorry, this is not to scale, but does not matter. This is the situation as far as complex poles are concerned, though the pole 0 configuration which I have given you is not to scale. Now, you just see in this particular case 1, 2, 3, 4, there are 4 poles, and therefore, there will be 4 root locus branches, k is equal to 0, k is equal to 0. These are the starting points. Okay. So, in this case I know that this particular portion will be on the root locus. I want you to make an attempt, first of all, to set an idea as to what type of root locus you expect. We will make the calculations later, and for that I make the pole 0 diagram so that it is properly scaled. So, if I take this 1 over here, 3, 1, 2, 3, 1, 2, 3, okay, roughly, okay, hopefully this is better picture compared to the earlier situation. So, you find that in this particular case, this total is on the root locus. So, naturally one branch starts from here, k is equal to 0, other branch from here, k is equal to 0, one more branch, k is equal to 0 here, and a k is equal to 0. This being complex poles, one thing I want, that the direction at which the roots are going to depart should be known to me, because there are so many possibilities, and out of those possibilities one of the possibilities should be set, and this is one of the, I may not be applying the rules in the order in which I have given you. Okay, let us set the direction phi p. How do you calculate the phi p? Please see, this angle you will take up, this angle and this, and all these will be with negative signs. So, the phi p angle is going to be plus minus 180 degrees, minus this angle, minus this angle, minus this angle, and the result available with me, which may be wrong because after all it is rough graphical calculation, you can check it, but I will give you the numerical values which I have got. It is minus 71.6 degrees is equal to phi p. Okay. Applying the formula I have given you, the phi p comes out to be this way, and therefore, now I know that if this is the angle I take, well, roughly this branch goes this way, and by symmetry rule this branch goes this way. At least the angle at which they depart becomes known to me. It is minus 71.6, and by symmetry I am taking the other angle. Okay. Do raise a question to me please directly if there is any doubt. Fine. Now, I was asking you as to what is the rough sketch you can make. Probably before you suggest the rough sketch, let us see the angle of asymptotes and the centroid. From that point onwards, I am sure the rough sketch will automatically emerge in your mind. The angle of asymptotes formula you apply and give me, some of you might have calculated. Please give me the angle phi a. Yes, anyone who has calculated? Otherwise, I write from my notes 45, 135, 225 and 315. These are the 4 angles you are going to get, because n minus m is equal to 3. Q will be equal to 0, 1, 2 and 3. I will give you the formula if you want. Phi a equal to 2q plus 1 180 degrees over n minus m, q is equal to 0 to n minus m minus 1. So, this formula, application of this formula will give you 45, 135, 225, 315. Okay? N minus m is 3, n minus 4 minus 1. 4 minus 1 is, yes, 4 only, yes, I am sorry, yes, n minus m is 4. So, n minus m minus 1 is 3. So, q will be 0, 1, 2, 3, 4 angles. You are right, and the 4 angles I have given you. Now, let us see minus sigma a, the centroid. This is sigma real parts of poles. In this case, no zeros, so let me not write it, divided by 4, 4 poles, n minus m is 4. Now, I will not make an error. Real parts of poles you can check, minus 1, minus 1, minus 3. So, total is minus 5 by 4. So, you get minus 1.25. So, it means your asymptotes now are available at minus 1.25, somewhere here, angles yes. Are you getting an idea now with these asymptotes before you as to what type of root locus are you expecting? You see, after all, these asymptotes are the 4 directions for the root locus branches, there is no 0 available. So, the 4 root locus branches will terminate on these asymptotes only. So, though you see it is to be proved, but it appears that this root locus branch may go this way, this root locus branch this way to infinity, and there may be I say a breakaway point somewhere here, so that one root locus branch goes this way and the other goes this way and the root locus plot is complete. This is intuitively this feeling comes from looking at this particular picture. Intuitively it should be clear that maybe the root locus will go this way only, and therefore, to see that, the next rule I have to apply is the breakaway point calculation. So, if I calculate the breakaway point in this particular case, you recall the relationship for the breakaway point. This is your GS or Fs, whatever you call it. Your breakaway point is dk by ds equal to 0. What is k? K in this particular case is minus sign you can take, but minus sign is not important. S into s plus 3, s squared plus 2s plus 2. This is your k. Okay? 1 plus gs equal to 0 will give you this value of k, taking all other terms on the other side. Now, you have to set dk by ds is equal to 0. So, in this particular case you find that dk by ds will turn out to be a 3rd order polynomial. So, solving a 3rd order polynomial is difficult. So, I hope with the calculator available with you, you will be able to roughly get a value of, you see, of one real value. You see, you expect one breakaway point. You just see that. From the root locus plot it appears, you expect one breakaway point. The other 2 points which will turn out to be roots of the equation dk by ds is equal to 0 are hopefully not the breakaway points, as is intuitively clear from the root locus plot. However, if you are sitting on the computer terminal, you will immediately check for the other breakaway points. But if you are doing it by hand calculations, then this guideline is also good enough, that you try for one real root of the equation and that location of the real root also roughly you know that it should be somewhere in this particular region, and hence the breakaway point can be calculated. The answer available with me is, for example, the complete answer minus 2.3 minus 7.725 plus minus j 0.365. You see that these are the roots of the equation dk by ds is equal to 0, which you find is a 3rd order equation. So, this is one root of that equation minus 2.3, and these are the other roots, and you can see now these 2 roots are not the breakaway points because they do not lie on the root locus branches. You can even apply the angle criterion on these 2 points, you will find that the angle criterion is not satisfied. You see, after all, if we are making the rough root locus sketch, we are not saying that, well, the computer is so costly that we cannot afford the computation. The idea is this, that we want to get a quick glimpse of the total problem. Even if there is a little error here and there, it does not matter, because the final design definitely you are going to make sitting on using the CAD software. So a rough calculation is necessary, so that you can, when you design it on the computer, so there is no error there, because the rough idea of the total problem is available with you. And this concept will follow in the examination also. Please see, I will not worry about the very exact values. So I will worry about the logical sequence you have followed as far as the analysis or design problem is concerned. So in this particular case, for example, you find minus 2.3 appears over here. This is the breakaway point, and hence logically the root locus branches will go this way. Okay. You see, in this particular case I have taken a little more comprehensive example, but from the point of view of illustration, simple example could have been taken where the calculations are less. But here all those points which I want to explain hopefully will become clear. All the rules will come up in this particular example. Fine.
So you said minus 0.725 plus minus j 0.335 is not a breakaway point because it does not lie on the locus.
That's right.
But that is only from intuition. It could lie.
Yes, that is what I say, that
So
by intuition, because I expect that this will go this way. If you say it could lie, the only check is this: take the point and apply the angle criterion. After all, the point you have calculated, my intuition says that it won't lie. If you don't agree, quantitative evaluation is possible. Take a point and on that, because angle criterion requires all the open loop poles only, take that particular point and apply the angle criterion and satisfy yourself. Okay. Now these root locus 2 branches we have already calculated. Go to the other 2 branches. As I said, my intuition says, though you can check, that it should go this way. Now to make a rough sketch without going to any calculation, one point I know is the angle of departure. If in addition I know this point where it is going to cut the imaginary axis, maybe the rough sketch which I am going to make will be more accurate. And the point where it cuts this particular axis can easily be calculated using the Routh-Hurwitz criterion. Since I have already explained the Routh-Hurwitz criterion to you, let me not redo it on this example. Let me give you the result. I find that as far as this point is concerned, it is j 1.1 and corresponding k is 8.16. Coming from my notes, please. K is equal to 8.16, starting from k is equal to 0. K is equal to 8.16 makes it oscillatory, and larger values of k will make the system unstable. And the corresponding roots of the auxiliary equation which I have found are plus minus j 1.1. So if this point is also available, an angle of departure is available, in that particular case a rough root locus sketch can be drawn. Okay? Any question, please? Now if this is okay, yet my discussion on this example is not clear, not complete. Let me say, how do I use this information? I have taken this as minus 1, this as minus 1, this as minus 1, this as minus 3, and let me say that these are the no, there is no pole here, sorry. This is the root locus sketch you have already made, but please note that you cannot take any quantitative information from this sketch unless it is the quantitative information is required only at these points which you have made, for which you have made exact calculations. Otherwise it is a rough sketch. Any quantitative information you want to take, you see, you have to test the validity of this sketch by application of angle criterion. For example, I want you to give me the value of k. Recall, the open loop transfer function was k s into s plus 2 s squared plus 2s plus 2. I want you to give me the value of k so that the closed loop system has got damping equal to 0.6. Come on please, help me, how will you do it? You know that damping equal to 0.6 is a line corresponding to this zeta equal to 0.6 line, it is called. where theta is equal to cos inverse zeta. So, you make a line in the S plane. Now, my design problem starts, please. It is the design problem now I am making. It's a simple design problem, only gain adjustment. The PI, PD, other controllers I have not taken. Only the amplifier gain can be manipulated. And my question to you, design question to you is this, that give me a suitable gain K. Adjustment will be done using amplifier, so that the closed loop system has a damping of 0.6. So, the starting point is this, that I draw a damping line. See the procedure, please. So, this damping line intersects this particular root locus at this point. So, this is a candidate as far as the root locus point is concerned, but not necessarily a root locus point, because I really do not know whether this point satisfies the angle criterion. It is surely a candidate, because a rough sketch was made. Okay? Now, how to check whether this is a point or not? In that particular case, at this particular point, I will apply the angle criterion. If the total angle contribution at this particular point due to all these poles is an odd multiple of 180 degrees, in that particular case, this point fortunately is a point on the root locus. If it does not, then your rough sketch does not pass through this point, and you have to make an adjustment in your rough sketch, so that this point or a point close by is a point on the root locus. Where do you try? You cannot try here and here, because you want zeta is equal to 0.6. So, it means your trial of points is dictated by this line only. So, you take a point here or here, depending upon whether angle is plus or minus. Whether you want to increase or decrease the angle, that will become clear when you make the root locus sketch from here, when you apply the angle criterion. So, your trial point is along this line, because you want a point on the root locus for which zeta is equal to 0.6. So, make a trial point and see that the angle criterion is satisfied. So, let me save time over here. Let me assume that all the trials have given you this particular point. Okay? And now, let me go to my notes. This particular point, well, in my notes the calculations have been made for zeta is equal to 0.5. The point is, this particular point is minus 0.4 plus minus j 0.7. Plus minus j, it means these are actually the closed loop poles of the system. See this particular point, zeta is equal to 0.5. This particular point gives you closed loop poles of the system, and the corresponding value of k as per my calculations is 2.91. Help me please, how do you calculate k? I have already given you the idea. The k calculation will be done by applying the magnitude criterion. At this particular point, this distance into this distance into this distance into this distance is the value of k, because there are no zeros. In general, k is equal to s plus p1 magnitude, s plus p2 magnitude divided by s plus z1 magnitude, s plus z2 magnitude, and so on. Now, this is the point under consideration. So, s plus p1 is this distance drawn to scale, the scale of the graph which you have already taken. So, do not do this calculation, otherwise you can do these calculations. You substitute your s value over here and do it analytically, but graphically it will go better. After all, if you have to spend this much of time in analytical calculation, better you go to the computer. So, graphically a quick answer can be obtained by taking this value into this value into this value into this value. Since there is no 0 here, the denominator will not have any value. So, denominator is 1. Okay. Otherwise, in the denominator corresponding magnitudes would have come. So, the value of k can be calculated over here, and as per the notes here, the value of k turns out to be 2.91. Okay. So, the value of k is 2.91, and the corresponding closed loop poles are minus 0.4 plus minus j 0.7. Now, this corresponds to the value of zeta equal to 0.5. Now, under consideration, as I told you that it is a comprehensive example, well, it has all the ingredients which are needed in a root locus design. So, do not worry about the complexity. What are the other things? The other things are finding the other two closed loop poles. After all, it is a fourth order system. You have found the two poles, and you know that the zeta equal to 0.5 has a meaning only when the other two closed loop poles are insignificant. That is, these two poles are dominant in nature, and for that you require the location of the other two closed loop poles. How to determine the other two closed loop poles? Please see, one of the poles is going to start this way, one of the root locus branches. The other root locus branch is going to start this way. So as k increases, one root locus branch is going this way and going this way, and as k increases, the fourth root locus branch is going this way. So it means you want 2 points on these two root locus branches which correspond to k is equal to 2.91, because k is equal to 2.91 is the value of interest to you. So it means now you think of the procedure. You want 2 points on these two branches which correspond to k is equal to 2.91. Using computer you will immediately do it, but by graphical methods it's trial and error. You see that you can take a point over here, apply angle criterion or apply magnitude criterion on this particular point and calculate the value of k, and by trial and error find a point which roughly gives you the value of k is equal to 2.91. Okay, so it has to come graphically through magnitude criterion only, but you see, since very rough values are acceptable in the design, so this is not going to take lot of time and you can hopefully make these calculations, and the value available with me is minus 1.4 and minus 2.85. These are the two values, please see. So it means the two roots are the real roots corresponding to k is equal to 2.91. It does not go to these branches corresponding to these roots. This was your one value, this is minus 1.4, a pole over here. This how much was the cutoff point, please? I don't remember. Should I take it this way? Naturally I have to take it this way. So here it is minus 2.85. So you see that for the closed loop system these are the 4 poles, and you find that your dominance condition is not satisfied, because the real portion of the complex conjugate poles is 0.4 and the other poles is 1.4. It is roughly 3 times away and you want roughly 4 to 5 times away. So naturally this total analysis will come from simulation, but you have a rough idea that whatever peak overshoot you expect corresponding to zeta is equal to 0.5, the actual overshoot will be slightly more than that because of the presence of this, will be different than that, not more. You see it, what will be the effect of the pole, please? It depends what is the effect. It depends upon the relative residues. As far as the 0 is concerned, it gives a pronounced peak, but a pole does not necessarily give a pronounced peak. It depends upon the relative residues. So I make a statement that the peak overshoot corresponding to zeta is equal to 0.5 may not come up because of the presence of these nearby poles, and hence it will be clearly shown by the simulation exercise only. And you have to enter into the design cycle suitably so that the complete acceptance of the response of the system is guaranteed as far as user requirements are concerned. So in this particular case I say that the overall for k is equal to 2.95, the overall closed loop transfer function has the poles and zeros like this: 2.95 over s plus 1.4, s plus 2.85, s plus 0.4 plus j 0.7 into s plus 0.4 minus j 0.7. These are the closed loop poles of the system corresponding to k is equal to 2.95, which you have taken corresponding to zeta is equal to 0.5 value.
So graphically, can we get 2.91 accurately?
Not, this is what I said, that probably you cannot. Yes, you can, provided you have that much of patience, and it is difficult to have that much of patience, and therefore it is the rough calculation. After all, you want to check the dominance condition. Even the dominance condition is not quantitatively known, so it is a rough estimate that where does the pole lie. Okay, so that is why I am making a statement that all this exercise you may laugh at, thinking that when computer can do all these for you, why should you do it graphically or analytically? But really it is useful as a learning module. Once you learn all these things through this particular process, then you can appreciate or analyze the computer graphs very quickly and easily, and the chances of errors are reduced there. Okay, that is the purpose. So I don't say that, even that is why I made a statement, don't worry, from the examination point of view also, you just outline the procedure very clearly. Now 2.91 you should not end up with, for example, 0.9, that will be too approximate. 2.91 if you end up with 2.5 or 3, well, it's fine, it's fine. 2.5, 3, even 3.2 chalega, doesn't matter. But you should appreciate, you should understand, and you should say that, because for want of time you are giving the procedure. Okay? Fine then. I think with this example all the rules probably have been given to you very clearly, and let me take a couple of more examples, and then next lecture will be completely on design. The other example I take is the following: Ka S into S plus 2, it is a tachometric feedback. You can imagine this to be a position control system with tachometric feedback. So there are two variables I am taking, Ka the amplifier gain and Kt the tachometric constant, R here, Y here. I want to design this system for a specified value of zeta, for example. Okay. Resolving this into a single loop configuration, you see I can easily get this diagram. Please help me whether this is okay. Well, let me write it separately. It will be Ka over S into S plus 2 divided by 1 plus Ska Kt over S into S plus 2. So this gives me Gs over 1 plus GSHS. This gives me Ka here divided by S squared plus 2S plus 2 plus Ka Kt into S. I hope this is okay. In case of error, please do help me. YR. I have resolved this into a single loop configuration. Inner loop has been resolved, and resolving the inner loop I get this as the equation Ka over S squared plus 2S, this S damping term I have added to this, so that this becomes the overall configuration of the system. What is the characteristic equation? The characteristic equation in this particular case turns out to be S squared plus 2 plus Ka Kt S plus Ka equal to 0. Please note this point now. I have given this idea to you earlier that poles and zeros of the system may be different than the poles and zeros of the open loop configuration given to you. In this particular case I put it in a different way: S squared plus 2S plus Ka plus Ka Kt S equal to 0. Putting it in this form, 1 plus Ka Kt S divided by S squared plus 2S plus Ka equal to 0. If I am interested in studying the variation of Kt, I will like to put Kt as a multiplier as far as the Fs function is concerned. So you will see that this function has been formulated as 1 plus Kfs equal to 0, where your K is the root locus gain, which is equal to Ka Kt. Assuming that Ka, the amplifier gain, is known to me, in that particular case variation of Kt can be studied with respect to this particular equation. So you please note that 1 plus Kfs is equal to 0 is an equation where K is the root locus gain, and this root locus gain you have to bring out suitably as a multiplier, and this is that value which you want to vary to study the effect of that particular parameter. A question to you: Ka is equal to 60. Give me the value of Kt so that damping is equal to 0.5. Come on, make an attempt please, quick. I write the characteristic equation again: 1 plus 60 Kt S divided by S squared plus 2S plus 60 equal to 0. Ka is equal to 60. The amplifier, I am taking one parameter at a time. So the amplifier gain Ka is fixed. In that particular case, I get this as the suitable characteristic equation suitable for making the root locus sketch. I want you to give me the value of Kt so the damping of the overall system is 0.5. So I need the root locus sketch for this. Now poles and zeros are not necessarily the poles and zeros of the original system, they are the poles and zeros of the root locus function. So in this particular case you find a 0 at this particular point, and there are two poles which are complex conjugate poles. And now I leave this as a simple exercise to you. If I have the values in my notes I will give you, otherwise the general sketch. I think let me give you the general sketch. This is on the root locus. The root locus in this particular case is going like this. Here is the break end point. These are the two root locus branches. Okay. A simple exercise for you to prove that in this particular case the root locus branches, complex root locus branches are in fact part of a circle. Okay. This I leave it to you, but suppose this is drawn in this particular case. What is the net exercise? The net exercise is to draw this particular line at zeta equal to 0.5. Let me see if I have the result. Yes, I have the result available. Zeta equal to 0.5. Okay. Now, corresponding value of k can be calculated. From that k, kt can be calculated. Kt is equal to k by 60. The result is kt is equal to 0.0958. For those who may try this example, I am giving this result, otherwise the procedure is good enough. 0.0958 is the value of kt at this particular point. Remember that the k parameter is 60 kt and not kt. You have to calculate kt. The root locus gain in this particular case is 60 kt. The value of ka is 60 and kt can be calculated from this. So, corresponding to zeta is equal to 0.5, you can take this angle as cos inverse zeta, you can take this point, and from this particular point you can calculate the value of k and hence kt. So, this design has been made. Okay. Now, help me please, if I now change, any question please? I think it is analogous to the previous diagram, rather it is simpler. Now, my point is that if I change ka to 100, after all I assume that ka is also a variable parameter. If I make ka 100, can you tell me what type of root locus sketch you are going to get? I retain the earlier sketch also. Corresponding to k is equal to 60, what are the roots? The roots are here. Corresponding to k is equal to 100, can you help me with the real part of the roots? Just change k is equal to 100, real part of the roots is going to be the same, it is -1. Okay? Real parts of the roots is -1. So, corresponding to k is equal to 100, the open loop poles of the function fs are the following. And therefore, if the original root was like this, corresponding to k is equal to 60, now the root locus diagram will appear like this, corresponding to k is equal to 100, and hence the two branches now will appear like this. One is going this way, the other is going this way. Now, if you want to investigate what is the value of kt when ka is equal to 100, procedure is same, write the zeta line. The only thing is that now instead of investigating this point, you investigate the value of k, the root locus gain at this particular point, and the value of k which you get at this particular point divided by 100 is the value of kt. So, if you have visualized, slowly I have given you a procedure of using the root locus for studying the effect of two parameters instead of only one parameter. So, you see that initially it was only one parameter varying. Now, I have two parameters ka, the amplifier gain, and kt, the tachometric constant varying. I find that for k is equal to one value, the two roots are here, for ka another value, the two roots are here, and the root locus branches are changing this way. So, I can call these roots as root contours. Instead of a root locus plot, these I say root contours. You see that this each portion of this root contour is a root locus plot for a particular value of one of the parameters, the other parameter varies. So, you can say that actually if you consider the denominator s squared plus 2s plus ka equal to 0, this particular line is actually nothing but the root locus plot of this particular equation. You can check this please. So, it means the open loop poles of the function 1 plus fs is equal to 0 are in effect the closed loop root poles of this particular function are the roots of this particular equation s squared plus 2s plus ka equal to 0. Corresponding to ka is equal to 60, your two roots are here. Corresponding to ka is equal to 100, your two roots are here, and so on. So what you have done in effect, or let me take the next slide. If you have two parameters ka and kt, 1 plus ka kts divided by s squared plus 2s plus ka equal to 0. If you have those two parameters ka and kt, the procedure now is the following. First of all, you concentrate only on this denominator, which is a function of only one parameter, and you will note that the roots of this particular equation are the open loop poles of the total function, open loop poles. So it means first of all study s squared plus 2s plus ka equal to 0. Okay, this is a simple function, this is a simple quadratic function, so you could easily get the roots. But if it is a complex function, you can really put this also in a root locus format. This is 1 over 1 plus ka divided by s into s plus 2. Okay, so if I consider this s is equal to 0, this is minus 2, you know that the root locus is this as far as variation of ka is concerned. Though in this particular case I did not need this, because this was a simple quadratic, and a simple quadratic we could get the roots of this particular equation directly by solving a quadratic equation. But suppose this denominator itself is a complex function and there is only one parameter. So first of all you can get the roots of this complex function with respect to the change of that parameter by studying this equation and transforming this equation in the format of a root locus equation, and this is the root locus branch. Now once you have got this, this particular root locus gives you actually the open loop poles for the complete function, and then you go back to this, you take any 2 points of this, taking these as the open loop poles, you draw the total root locus branch. Take these 2 points, taking these as the open loop poles, you draw the two root locus. You could take these also, but normally you don't use your ka dat value. That is why coming to the practical values, I am taking the open loop poles on these lines and making the total root locus, and therefore for various values of ka which give you the open loop poles on this line, your root locus, your root contours are going to be like this. These are the root contours for various values of ka. For every point here k is equal to ka kt is equal to 0. For every point here k is the root locus gain, which is equal to ka into kt. But each point here or each pair here corresponds to one particular value of ka, because this total vertical line is the root locus of the denominator equation as ka is varied. So that way we can make the root locus contours of the system, and this gives us the method of studying the effect of more than one root locus branch on one parameter on the root locus plot of the system. Okay. The last point, I have a minute and a simple point. Let me take gs is equal to k e to the power of minus s tau d divided by s. It is the case of a dead time equation. Now you see that whatever method you have seen, the dead time has not come anywhere. So what you can do is, the dead time can be approximated by the Parday's approximation. So this can be written as tau d by 2s divided by 1 plus tau d by 2s. This is the approximation. Now if you see your pole 0 pair, please see, this can be written as minus k by s. Yes, naturally, yes, the pole is there. Yes, this is the function now. Now you see that bringing it in the standard pole 0 form, I can write this as, this is equal to s minus 2 by tau d divided by s into s plus 2 by tau d. You will please note the interesting feature in this particular case is the following. Your gs is equal to minus k s minus 2 by tau d divided by s into s plus 2 by tau d. So you see that if you write your function, it is 1 minus gs equal to 0. because there was this minus sign over here. So, what is your angle and magnitude criterion if the minus sign appears outside? The magnitude criterion remains the same, GS magnitude is equal to 1, but the angle criterion becomes angle GS is equal to plus minus 2q into 180 degrees. Now, you see it will become an even multiple of 180 degrees because GS is equal to 1 is your equation. Please see, your equation now becomes GS equal to 1. Earlier it was Fs equal to minus 1. Because it was minus 1, the requirement was odd multiple of 180 degrees. With this minus sign coming outside, it is an even multiple of 180 degrees. And if you take even multiple of 180 degrees, the rules will change now. 2q, wherever 2q plus 1 appears in the rules, it will become 2q because now it is an even multiple of 180 degrees. So, give me the root locus sketch for this example, please. I am sorry for delaying you a little. S is equal to 0 over here, pole over here, this is 2 by tau d here, this is minus 2 by tau d over here. Help me please, how do I make the root locus sketch in this particular case? You see, tell me whether this branch is there on the root locus or not. Apply the rule. No, as per the previous formula. Please see, 2q change, 2q plus 1 changes to 2q, but now because of the negative sign, you apply the angle criterion, you will find that all those segments which are there on this with even number of poles and zeros to the right are the branches on the root locus. These are the only changes you are going to make. You see, one, this real axis segment search, and the other, in all the rules 2q plus 1 is replaced by 2q. There is no other change. All the rules will exactly remain the same, but for these two changes, the real axis segment search and 2q plus 1 being replaced by 2q. So, if real axis segment search is changed, in this particular case you find that this segment is there on the root locus, this segment is there on the root locus, and therefore, your root locus branches are going to look like this. This is going this way, this is going this way, one is terminating at infinity, the other is terminating at infinity on this side. I hope this is clear. Just see, one is going this way, going to 0, the other is going this way, going to infinity. I again repeat, the only change is this in terms of real axis segment search and replacing 2q plus 1 by 2q whenever there is a minus sign associated with it, and this minus sign associated with it, an example is that of a dead time, which always gives you this particular value when you approximate it by a rational function. Thank you very much.